In continuation to our topic on flip-flop, today we are going to study about the introduction to JK flip-flop. As you can see, there is a circuit diagram, logic symbol, the truth table of SR flip-flop, and I have drawn the truth table of the JK flip-flop. We have already studied the SR flip-flop in detail in our earlier presentation, and we have noticed the disadvantage of SR flip-flop is mainly when both the inputs S and R are given as 1, because in that particular case it doesn't provide any outputs, and that becomes an invalid state in case of SR flip-flop. The same drawback or disadvantage has been overcome in the case of this JK flip-flop. So if we have a closer look at the circuit diagram of the JK flip-flop, here you can see that the output Q and Q bar, they are fed back as an input to the NAND gates 3 and 4. That is, the output Q is being connected as an input to the NAND gate 4, and this output Q bar is being connected to the input of this NAND gate 3. So thereby, earlier, which was SR flip-flop, making that SR flip-flop to be converted into the JK flip-flop. So this is how, by connecting these Q and Q bar outputs as a feedback input, the SR flip-flop has been converted to the JK flip-flop. Now let us consider the working of this JK flip-flop, which is similar to that of the SR flip-flop, with the difference being only when both the inputs J and K being given as 1 1. So let us see when we are having the clock 0. So in that case, let us see when there is no clock, and here we are getting as 1, here also we are getting as 1. And if you can recall the NAND latch, when both the inputs are 1 1, in that case there is a memory state. So here we are having the memory state when there is 0 clock. Next, when we have connected the clock is 1, and when both the inputs J and K are 0 0, in that case also again when clock is 1, and when both the inputs are 0 0, again we are getting here 1, here also we are getting as 1. So again the NAND latch where both the inputs are 1 1, we will have the memory state. Next, in similar manner, now when clock is 1, when J is 0, K is 1, in that case J is 0 and K is 1. So here we are getting as this is 0, this is 1, and so here we have now 1. So when this is 1, here we are getting as 0, and the NAND latch in the case of 1 0, it gives us output as 0, Q output to be 0, and complement out to be 1. So we are having 0 1, and similarly in the case of 1 0, we have 1 0. Now comes our main input, that is when both the inputs J and K are given as 1 1, and let us see how we are going to get this output as complement of the previous state. So for that we have to consider either Q is equal to 0 or Q bar as 0. So in this case 1, let us see now when J is equal to 1 and K is equal to 1, and I have assumed here Q to be 0, and let us see what the output is going to be now. So coming back to the circuit diagram, we are having J is equal to 1, K is equal to 1, the clock is 1, and now we have taken Q to be 0. So this is 0. So as you can see, this Q 0, it goes to the, so here we are getting 0, this is 0, this is 1, this is 0, this is 1, this is 1, and here we are having Q bar as 1. So here we are getting 1, this is 1, this is 1. So here you are getting as 0, and here you are getting as 1. So again, now when we recall the NAND latch in which the inputs are 0 and 1, in that case we get output as Q equal to 1 and Q bar equal to 0. So here we are getting output as Q is equal to 1 and Q bar is equal to 0. Now if you consider the case 2, in which J is equal to 1, we have K is equal to 1, and if we assume Q to be equal to 0, now in that case, Q to be equal to 1. So now we have Q equal to 1, the second case. So here now Q we have 1, and this is okay. So this will give us, when this is 1, now here we are having 1, all these three inputs are 1, and here we will have as J as 1, clock as 1, and 0. So now here we are getting, this is as 1, this as 0. So the NAND latch, when the inputs are 1, 0, it produces outputs as 0 and 1. So when we have 1, 0, it produces 0 and 1. So it is quite clear from both the cases that what we are seeing is that when the output was 1, it is transferred to 0, and from 0 it is transferred to 1, and similarly the Q bar output, it was 0, it is transferred to 1, and from 1 to 0. So in this way the output is getting toggled, and mainly this is not toggled, it is known as race around condition, and this race around condition is a very important topic which we will discuss in our later on in presentation on the master slave flip flop. So this is all about the JK flip flop. Thank you.